Hi, good morning, everyone. I'm Zhaozhou, Marie Curie Fellow from Hebrew University. It's a great pleasure to see you again here. This is my second day in Santa Cruz. So thank you, everyone, for making this conference possible. Today, I will present our ongoing work, an accurate new analytic model for the structure evolution. The evolution of galaxy, the stars and the dark matter in the galaxy in response to many dynamical processes. And I will show you how this model can help us to model the formation of dark matter deficient galaxies. Let's start. Yeah, as you know, the lambda CDM cosmology has a great success in explaining many observations, especially on the large scale. However, still facing some challenges in small scales, especially in reproducing the diversities in galaxy structures. One famous example is the so-called cusp core problem. In dark matter-only simulations, we usually see the dark matter profiles follow a very cuspy shape, while in observation, many of the galaxies are observed to have chord shape. This has raised a lot of curiosities. People argue that maybe this is a hint that we need alternative models for the lambda CDM cosmology, like self-interacting or decaying dark matter and other models. In Fanzo's talk, he will talk more about this. But we have to, I'd like to emphasize that, don't forget that we must consider the baryonic processes, especially the supernova feedback, aging feedback, etc. Those processes can change the potential of the halo and make the dark matter and the stars to redistribute. This is also related to the dark matter fraction in galaxies and the galaxy size. Take an example. There is a category of interesting objects named ultra-diffuse galaxies. They have stellar mass comparable to normal dwarf galaxies, but with a much extended stellar distribution. So those feedback processes like supernova feedback can push out the dark matter. Meanwhile, it can make the stellar system puffed up as well. And in the extreme case, people found that in some of the ultra-diffuse galaxies, the dark matter mass is a factor of 10 less than the usual expectation. That's the famous DF2, DF4 galaxies. A popular explanation for that is the dwarf galaxies can get puffed up by supernova-driven outflows in the field, and then the tidal evolution in groups can further amplify the diversities of its structure. Of course, there are alternative solutions. See other talks today. Another related question has been recently raised by observations at high redshift and for massive galaxies. Reinhard Genzel and his team measured the rotation curve of massive galaxies at redshift 2. While most of the galaxies are shown to be dark matter dominated, a significant fraction of these seems to be baryon dominated. This is put it in another way. Here, this figure shows the dark matter fraction within the effective radius of the galaxy and versus the maximum rotation velocity. In contrast to those low redshift galaxies, the high redshift, not really high, redshift 2 galaxies seems to have a much lower dark matter fraction within the galaxy. This is very surprising because those processes like supernova feedback, which is can effectively push out dark matter in dwarf galaxies, are not so capable in those massive halos. And such cold massive galaxies are not reproduced in current hydro simulations, which might be related to the resolution issue and improper subgrid physics. Avisha proposed a hybrid scenario for the core formation of those massive galaxies. So the galaxies can be first heated by dynamic friction of infalling satellite galaxy. Due to the dynamic friction, the satellite galaxy will transfer its orbital energy into the kinetic energy of the host. In this sense, the dark matter and the stars in the galaxy in the host will get heated. Then the host system becomes more responsive to the subsequent aging-driven outflows. And our collaborators has put much efforts on this and proposed analytical models for to trace these processes, like SATGEN and Zhaozhou. However, there still are some unresolved issues. The first is, while the satellite can hit the host, it also brings more dark matter. So which process is the more dominant one? Also, we would like to know the differential response of stars and dark matter to outflow. We want to push out dark matter while keep the stars in the system to get a dark matter deficient galaxy. Also, we are interested in the consequence of repeated gas outflow-inflow processes. So to recap our task, there are many processes that are ongoing: merger, mass accretion, feedback. So a galaxy is really a chaotic place, and there are many drivers for the structural evolution of the galaxy. And we can summarize them into two categories: the mass changes due to accretion and feedback-driven outflows. Also, for a satellite galaxy, it can suffer from run pressure and tidal stripping. And another kind of perturbation is the dynamical heating by mergers, or the satellite will suffer from the tidal heating from the tidal field of the host. So I should emphasize that in these chaotic processes, neither the energy or the actions are conserved. So it's not easy to model these processes accurately. Here, this slide, I would like to give you some idea how the dark matter the gas outflows can push out dark matter. So we know that dark matter and baryons do not have directed interactions in the standard model. They can interact through gravity. So initially, we consider a star or dark matter in the potential of galaxy. It cannot move. Its motion is limited to a certain radial range due to the potential wear. So if the gas outflow happens, then the potential will get shallower. The dark matter particles or star particles will move to more extended orbits and spend more time on the outskirts on average. As a result, we will get a lower density or in the center. Very good, but this is not the end of the story, because the redistribution of the matter will lead to the redistribution of the orbits. So we have to solve this in an iterative way. This is actually the famous violent relaxation process. After this, it will reach to a new equilibrium. The violent relaxation has been a long-standing problem since Lynden-Baer for more than 50 years. Note that neither energy or actions are conserved in this process, so it's really a theoretical challenge. And here we proposed a new model for that by following the evolution of distribution function of the system in a statistical way. I won't bother you with math, but I'll show you some idea how we implement it. We start from the initial equilibrium. Then a galaxy can perturbed by mass changes or dynamical heating. Then we have to follow the evolution of the energy distribution all the way in iteratively. Then let's see how it works. Here I show you an example. Here is an NFW halo with a gas component inside, which is not shown. Then we can add more gas into the system. The dark matter halo will get contracted, as shown by the red line. Or the system can, if we, due to feedback, we eject the gas from the system. Where is the arrow? The dark matter will get halved up and form a dark matter core. Note that here the solid line is the unbody simulation result, and the dashed line is our model prediction. You can see the very good consistency between the model and the idealized unbody. And here is a comparison with different models. Here again, I show you the density profile of the dark matter under different changes of gas. Doubled or removed gas from the system. I show you the y-axis in density times radius for the larger dynamic range. So here, this is our model, and we can see if we assume the adiabatic invariance or energy conservation, we cannot well reproduce the core formation. Okay, then our next question is to we have seen how to lower the dark matter density in a galaxy. The next question is we want to push out dark matter but keep the stars in the system. How is that viable? Here on the right, I show you our model prediction and in comparison with the unbody simulation. Here it shows the density profile of stars and dark matter in equilibrium initially in a galaxy. There is a gas component in the system. Then we push out the gas, and you will see how the dark after the system re-establishes the equilibrium. The dark matter density drops a lot, while the density of stars only changes a bit. That's a way how we can create a dark matter deficient galaxy. The reason behind is that because the dark matter is much more extended and that's more responsive to outflow and dynamical heatings. Okay, now we can put those stuffs together. Here I will show you how we can combine the dynamic friction heating and the multiple ellipsoid gas outflows. We start from the initial NFW profile. So the y-axis, I show you the dark matter mass within the initial effective radius of the galaxy. So we start from 1. Then after dynamical friction heating by a merger of 10%, the dark matter density drops a bit. Then we push out 90% of the gas from the system. We see the dark matter density drops a lot. And we can get even stronger reduction of dark matter density by repeating gas inflow-outflow processes. Then we can reduce the dark matter density by another factor of 2 after multiple ellipsoids. The same mechanism can apply to explaining the dark matter deficient high redshift galaxies or the formation of ultra-diffuse galaxies in the field. Of course, this depends on the specific gas formation, the gas mass history in the system and the orbits of the mergers. And for the galaxies in group, we would further consider the tidal evolution. Now I quickly show you a comparison with the observation. So here I show the blue circles as the Ganzos sample at redshift 2. Here I show you the dark matter density within RE versus the effective radius following the suggestion of Andy Burkett. And here you can see the observation, the dark matter density is lower than the expectation of NFW profile or those from TNG simulation. And this gray circles show a mock sample following the standard scaling relations and NFW dark matter profile. Then we added the gas outflow and dynamical heating. You can see that the system, the galaxies get puffed up and the dark matter density drops a lot. If we add multiple gas outflow, then we can get something very close to the observation with reproducing those low dark matter fraction galaxies. And also, we should consider the sample selection in observation. And in this figure, I show you the comparison between the dark matter fraction versus the effective radius, stellar mass, and the bulge between our observation of Zhaozhou and our model prediction. So you can see a general consistency between the two. Okay, we have talked about the galaxies in field, and for those galaxies in group, we need to further consider the evolution of satellite galaxies. There are many interesting questions can be asked. What are the fate of those satellites, and how the stars and the dark matter get stripped differentially, and how the tide can amplify the structure diversities. The unbody simulations are very useful, but they are slow and costly. So we can build our model. Analytical model can also apply for the tidal evolution. Here I show you how the dark matter profile evolves under the different tidal strengths. On the left is a Caspi subhalo, and on the right is a Chord subhalo. And also we can apply the model to multiple component systems. So from a system of stars plus dark matter, and we can see the dark matter density evolves much faster than the than the stars. So in a consequence, it will lead to a dark matter deficient system, satellite system, when the satellite is get severely stripped. Okay, I will stop here and leave you the summary. We built a general model for the structure evolution with outflow, dynamic heating, and tidal stripping. And we expect it to be useful. Okay, thank you.
Hi, my name is Viraj. Thanks for the very awesome talk. I had two small questions. First, is there like any assumption of like how much inflow versus outflow, like what the ratio between the two is? Like for instance, could you have a huge inflow that would, I guess, overcompensate for the effect of the outflow and not cause this small decrease? Yeah.
You mean a huge outflow concentrate?
Oh, so I mean, so in your model, the outflow causes the inner dark matter density to go down, and inflows cause it to increase.
Yes.
So I was wondering, is there some assumption of what
we assume that the same amount of inflow and outflow. The key is this process must be very fast. Must be much shorter than the local dynamic time. So even you add the same amount of gas back and take it out, after multiple iterations, the net effects will accumulate. You will get a lower dark matter density in the end.
Okay. So
the key is the system. The process must be quick to break the invariant, the adiabatic invariance.
Okay. So a quick follow. So basically, does that mean that outflows are more efficient at decreasing dark matter density than inflows at increasing dark matter density?
Yes.
Okay. Cool. Thanks.
Okay.
Hi, this is Hao-Wen. So nice talk here. I just have a question about the outflow. So somewhere in the talk you mentioned that the outflow is from AGNs, right?
Yeah.
So have you compared these the outflows that you implemented in your model with typical properties of AGNs at similar redshifts?
Sorry, you mean this?
In other words, like, do you assume the typical outflows that you would see for the galaxies at this mass, at this redshift, or there's?
We made a very simplified assumption. So we assumed some standard gas fraction in the galaxy is about 3% of the halo mass ish. In observation, the outflow rate is very uncertain, so we don't know it clearly.
Okay, thanks.
Could the next speaker come up, and then we have time for a very quick comment from Avishai.
I just wish to make a comment that this model for dark matter deficient cores is nice, but I think it's not the main achievement in what Zhaozhou was describing. I think that Zhaozhou's work is a breakthrough in stellar dynamics, in dynamics of gravitating systems, in the sense that he presents a general way to follow analytically violent relaxation in systems. And there are many different examples, as he mentioned. One of them is this outflow and the effect of dark matter, satellite stripping, and so on. But there are many other. It's a very generic method that people can use for analytic modeling of violent relaxation, which is proven to be accurate according to simulations. So I think that's the great achievement here. And people are welcome to use it. Well, in general, it's a very general method, so far implemented in spherical systems. That's the easiest, the spherical cow for physicists. But I think it has the potential to treat any system which is taken away from equilibrium and then tries to relax us back to equilibrium. This system can be a disk. It will be a little more difficult to model, but it's a great challenge. You mentioned this before, and we took it into our attention. Yes.